Thank you very much. Thank you for this wonderful reception. It's such a great pleasure to be here, this magnificent hall. I'm going to report about a development that has kept me fascinated for many years. Now, ladies and gentlemen, we all know that seeing is, of course, central to perception. I don't think it's a coincidence that seeing is believing very much not only applies to our daily life, but it also applies to the natural sciences. And it's probably also not a coincidence that at the beginning of the natural sciences in the 17th or 18th centuries very much coincides with the invention of the light microscope. Because with the light microscope, we were able to see for the first time that every living being consists of cells as basic units of structure and function. And of course, with the light microscope, bacteria were discovered as major causes for diseases. And also subcellular organelles, such as mitochondria, were discovered with the light microscope. However, we also learn already at school that the resolution of a light microscope is fundamentally limited by the wave nature of light, to typically of 200 nanometers. And if you want to see smaller things, such as viruses, we have to resort to electron microscopy. Now, electron microscopy indeed has achieved a much higher spatial resolution, 10-fold, 100-fold, or even 1,000-fold higher spatial resolution. And in a number of cases, you can have a spatial resolution that goes down to the size of a molecule or even to the size of a single atom. And therefore, the question comes up, why do we still care for the light microscope now that it has this, say, fundamentally limited spatial resolution? Now, the answer to that question is actually given in the next slide, where I made a little experiment. Going down the library, I checked a journal that covers basic medical advancements, and I counted the number of studies in which a light microscope was used and those in which an electron microscope was used. And now you see which of the two methodologies won. And this relationship is actually quite representative. It's a fact that light microscopy still is the most popular microscopy technique in the life sciences. And there are two good reasons for that. Now, the first reason is that light microscopy is the only way by which you can look into living cells in 3 dimensions with minimal invasion, and also in living tissues. That's not possible with an electron microscope. And there's another reason, which is as important as the first one. To light or to electrons, all the proteins or biomolecules more or less look the same. But usually, we want to study a certain type of protein, a certain species of proteins, where it goes, what it does, how it interacts with others, and so we have to highlight it from the rest. In light microscopy, this is relatively easily done by attaching a fluorescent molecule, for example, to the protein of interest. Now, a fluorescent molecule has a wonderful property. It has 2 energy states, an energy ground state and an electronically excited energy state. And if you shine light on a fluorescent molecule, then the molecule can absorb a photon. In this case, it's green light and a green photon. Then it will be raised to a higher lying state, as you can see here. And there are some vibrational substates in here where some of the energy is lost in the wiggling of the atoms. But this lower vibrational state here is the so-called fluorescent state that lasts about 2, 3, 4 nanoseconds. And from that fluorescent state, the molecule can return back down to the ground state, emitting a fluorescent photon. Now, because some of the energy is lost in the wiggling of the atoms, the fluorescent photon is redshifted in wavelengths. It has a lower energy. And because of that, it's relatively easily separated from the excitation light, from the illumination light. And that makes fluorescence microscopy extremely sensitive. In fact, it is so sensitive that you can detect even a single fluorescent molecule, as has been discovered by WE. This is the ultimate sensitivity that you can imagine. However, if there is another molecule coming very close to the first one, or a second, third, fourth, and so on, closer than a distance of about 200 nanometer, it's not possible for the fluorescence microscope to tell the molecules apart. They look like a single blurred entity. So resolution is about the capability of a light microscope or of a microscope to tell features apart, to discern details to see them as individual entities. And this was, of course, limited by diffraction. Now you can imagine that a lot of information in a fluorescence microscope is lost, is not perceived, simply because the microscope cannot see the features, cannot tell the features apart. So anything that is below this structure, below the 200 nanometers, cannot be seen when it comes down to perceiving structural details. And therefore it's obvious that if you manage to overcome this diffraction barrier and can come up with a light microscope or a fluorescence microscope that has a much higher spatial resolution, much more information can be gained from the molecules, where they're located, what they do, at their real scale, at a molecular scale, at a nanometer scale. Now, in order to understand how we could potentially overcome this diffraction barrier, we have to understand the problem. And this problem can be boiled down to in very simple terms. Thanks. Now, the most important element of a light microscope is the lens and the objective lens. And the role of this objective lens is nothing but to concentrate the light in space. However, because light propagates as a wave, it's not possible for the lens to concentrate the light on a single geometric focal point. Rather, the light will be smeared out as a result of diffraction, forming a blob of light that is at least about 200 nanometers wide and about 500 nanometers along the optic axis. And this has a major consequence. All the features that fall within this blob, molecules, for example, will be flooded more or less at the same time with this illumination light, with this excitation light. And hence, they will also emit light, scatter light back, so to speak, at the same time, fluoresce at the same time. And if you put a detector here, and if we collect the signal that is produced by the molecules in here, you can imagine what happens. The signal will be confused. For example, if we see here the signal that is produced by this molecule, of course, it's also focused in here, it's also diffracted. You see, the signal from the various molecules will be totally confounded. So no matter what detector you place actually in here, could be a photomultiplier, could be the eye, or even a camera, you cannot tell the signal from these features apart. Now, the person who realized that diffraction poses a severe limitation to the resolution was this man at the end of the 19th century, Ernst Abbe. And he coined this diffraction barrier in an equation that is still named after him. It's saying that in order to be separable, two features of the same kind have to be further apart than the wavelengths divided by twice the so-called numerical aperture of the objective lens. That's just the refractive index times the sine of half of the opening angle in here. Now, this is a number such as 2 or 3, and if you put in the wavelengths of about 500, 600 nanometers, you end up with the 200 nanometers here as the best case. Now, this equation can be found in any textbook of physics, optics, of course, but also in textbooks of molecular biology or biochemistry because of the enormous relevance of light microscopy to these fields. And it can also be found on a memorial which was erected in honor of Ernst Abbe in Jena, where he lived and worked, and there you will find this equation written in stone. And this was accepted throughout the 20th century as, so to speak, the ultimate limit. Not only it was perceived as a limit, it also was a limit, to be fair. So in the 20th century, the best pictures you could get, for example, in the cytoskeleton, looked like this. Obviously, there is more information there if you can have a higher spatial resolution. That was the standard in the 20th century, but now we can do it like this. So there is clearly a difference that can be made today. And so what I'm going to talk about is how this transition actually from here to here happened, to make this as the new standard, so to speak. Now, well, when I was a student in Heidelberg at the end of the 80s, of course, I was very well aware of this equation. I said to myself, how can it be? Now we have end of the 80s, 1990, and this equation was coined in 1873. So much physics, so many new discoveries were made in the 20th century. In fact, I had to learn so many interesting phenomena, new type of things for my examinations. There must be at least one single phenomenon that came up in the 20th century that should be, say, useful for overcoming the diffraction barrier. For example, quantum mechanics came up, molecules and molecular states came up, and there is wells of new phenomena, of course, that should allow you to overcome this barrier. And at some point, I put it down in writing. So the notion was not to change the way the light is propagating, because I felt doing something just about the propagation of light is maybe not the way to go, but there may be an option in exploiting the properties of the fluorophores, the state properties, spectroscopic properties of fluorophore, or maybe there are quantum optical phenomena that can be used to overcome this diffraction barrier in the far field. So what does far field mean? So in those days, another type of microscope was already developed to a large extent, the so-called near-field optical microscope. And the near-field optical microscope changed the way the light is, so to speak, propagating at the object or interacting with the object, to be precise. So in this case, a very small tip at a nanoscale was used to confine the light specimen interaction at a very small scale. While this concept is definitely viable, it didn't allow, of course, to look into the interior of a specimen because it requires this tight interaction of the tip with the object. And of course, to me, to be fair, this didn't look really like a light microscope. I wanted to have something that looks like a microscope and operates like a microscope, meaning that has an objective lens. So I wanted to keep this concept of focusing. So what did I do? I checked out textbooks. And one day, when I was actually just across the Gulf of Bothnia here, the same latitude in Åbo, I opened this textbook on a Saturday morning, hoping to find something that would be interesting or useful to overcome the diffraction barrier. Then I came across this phenomenon of stimulated emission. I was instantly electrified, trembling. So, wow, I have to go back to a lab and make some assessments to see if this works out. Now I'm explaining to you why I was so electrified when I saw this phenomenon of stimulated emission. Let's get back to the problem. Now, as I explained, the job of the lens is to concentrate the light in space. But because we have this blob of light here that is at least about 200 nanometers wide, all the molecules here will be flooded at the same time with excitation light. No way out. We can't change that. However, while we can't change that, we may be able to change the fact that all the molecules that are flooded now with light are in the end capable of producing light at the detector. So if we manage to keep some of the molecules in a state in which they are not capable of producing light here at the detector, then we should be able to separate those that are the state in which they can produce light at the detector and from those where they can't. So the idea was to get molecules into a state in which they are not able to produce light at the detector and they're hence not seen by the detector. And then we should be able to overcome the diffraction barrier. So this is the top view now of the object. So the idea was to keep molecules in dark state. You see the properties of the fluorophore, the state properties of the fluorophore, that's the key idea, the states. Now you might ask yourself, are there dark states in a fluorophore? Is there such a thing? What is that? Now look at the basic energy diagram here of the fluorophore. This is the ground state and this is the excited state. Now, in order for the molecule to be bright, to fluoresce, it's clear, we have to get it to the excited state. If the molecule is in the ground state, it is dark. It cannot fluoresce. It has to be here in the bright state. So yes, of course, there is a dark state. It's the ground state. The ground state is a dark state, and the bright state of the molecule is the excited state. And we have that dark state inherent in any fluorescent molecule. It's just the lower energy state, it's the dark state that can, of course, in this idea be used to overcome the diffraction barrier. And so now you know what stimulated emission does. It does nothing but make dark state molecule. It gets molecule from the bright state to the dark state. And so the idea was very simple, and this is why I was so electrified. Use stimulated emission to keep these molecules in a dark state, or prepare the molecules in a dark state, despite the fact that they're flooded with the excitation light. If you manage to keep them in a dark state effectively, despite the fact they're flooded with excitation light, you can separate them. And now you know already how the STAT microscope works. We have the objective lens, we have the detector, this is a sample obviously, and we use now light for exciting the molecules, getting from the dark state to the bright state. And then, of course, if you look at the sample from the top, you have the diffraction blob of about 200 nanometers that is produced here by the excitation light, no way out. And normally, all the molecules here will be excited at the same time and then produce light here at the detector. And the signal here of all these fibers, this fiber, that fiber will be confused. You will not be able to tell it apart. And of course, a simple way of making a picture here would be to scan that spot just like this across the specimen, but the resolution will never be better than the size of that spot, as predicted by Abe. But now we would like to keep some of the molecules dark in order to have a higher spatial resolution. So what do? We use a beam of light that is redshifted in wavelengths, that is designed such that it turns molecules off, makes molecules go to the dark state, or makes dark state molecules, not bright state molecules, as the green one. Now, how can we make sure that the molecules are not excited by the red beam, but just de-excited, pushed to the dark state? Well, it's simple. You have to use photons with an energy that is not sufficient to excite the molecule, but according to very basic laws of physics or molecular physics or whatever, the red-shifted photon pushes the molecule from this bright state here, from this fluorescent state, back down to the ground state, to be precise, to a higher vibration level of the ground state from which it quickly decays. And then, of course, this phenomenon of stimulated emission takes away the majority of the energy, and a copy photon goes this way, but that's not seen by the detector. So from the detector perspective, it's dark. It's completely dark, and the molecule looks as though it would have never been excited. Because if you manage to make sure that the molecule gets instantly down after the excitation, it behaves as though it would have never been excited, ever have assumed the on state, the bright state. So one requirement is the redshift in wavelengths, but there's another requirement, which is also kind of trivial. Of course, you have to make sure that there is a photon interacting with the molecule. And not all photons that pass by the molecule will interact with the molecule. Most of them will just fly by, because the probability of interaction is finite. Technically speaking, there's a finite cross-section of interaction. But you can deal with that easily if you make the red beam bright enough, such that you can be sure that there is at least one photon, for sure, kicking the molecule down to the ground state, interacting with the molecule. Then you can be sure that in the case the molecule gets excited, it will definitely be de-excited. And this is actually shown here in the view graph. So this is the intensity of the red beam, and this is the ability of the molecule to fluoresce. And now I see if the intensity increases beyond a certain threshold that I put here more or less arbitrarily, you can be sure that there is, so to speak, a photon that gets the molecule to the ground state here with a probability of, say, 90–95%, and the molecule is unable to assume the on state. So you can say, if you have this intensity or higher, you don't need a high intensity, you need just that. But if it has this intensity, there is at least one photon there that for sure keeps the molecule off. And so you have a way of turning off molecules just by the presence of this beam. So here, if the intensity is IS or higher, the molecule is off, and you can put as much green light as you want. It won't be able to emit. If it's lower than that, it's on. So what do we need to do in order to see just that fiber, but not the other two, to separate it? Well, we don't want to turn all of them off. Doesn't make sense. Let's try to turn off this one and the molecules from there. So in this case, what we do technically, we modify the beam with a piece of glass that has a certain shape. We can modify it such that the red beam forms a ring. And now you can imagine that we can turn some of the molecules in the outer part, but you see, we can still cannot turn this one off and cannot that one off to see that one. So what do? You may say, okay, make the ring smaller, but that's not possible per se. You cannot make a smaller hole than spot. That is also limited by Abe's law. You cannot make the D as a whole smaller than the spot. But that is not needed. That's the critical insight. The only thing we need to do is we have to turn off the molecule. That's the trick by the phenomenon of stimulated emission. So what do? Well, you have to make sure that even here in this region, where the donut gets weaker in intensity, and of course it gets weaker the further in you go with towards the center of the donut with the red light, so that even here it's beyond the threshold. So we just make it brighter. We make the red beam brighter so that even at a point where it is lower in percentage, it is beyond the threshold in absolute terms. And now you see we can turn off the molecules here, and only the molecules that are here in the center are allowed to assume the on state, are allowed to fluoresce in the end. And this is what we want, because now we can discriminate this fiber from the other two fibers, because only the molecules of this fiber are allowed to be on, whereas the others are forced to stay off. And now we just do what we are expected to do. Just scan the beams across the specimen, just like that, and now we can separate the two fibers because the molecules are forced to emit time sequentially. Why time sequentially? Because we play this on-off game with them. So at the time this one was off, the other one was on, and vice versa, because we have this on-off game that is now inherent in this procedure. Just to make it clear, I'm removing the donut here to make a little point. All the molecules flooded here with excitation light, no way out. That's the result of diffraction. But only this subset is allowed to assume the on state. The neighboring molecules are forced to reside all the time in the ground state. So if you were to make a check here, which state are they in? Check, 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 all the time. You will find them in the ground state. Because as soon as they get up, they're instantly pushed down, so you would always find them here in the ground state. And because we have now two classes of molecules, ground state molecules and excited state molecules, we can separate them and tell the features apart at subdiffraction dimensions. Now, this is the concept, but in the end you have to show that it works. There was a lot of development showing that it works, and I would like to show you what is possible today, for example. Now, you have here the standard resolution, confocal, I should say. This is a technical term, means the best possible, even better than the normal say, epiphoresis that you have. So this is the highest end of the 20th century, and now this is a comparison with stat microscopy. Now you really see what it is. Because the resolution in the red channel, at least, was increased roughly by an order of magnitude, and because the resolution is so high, you see now that this protein complex consists of, has an 8-fold symmetry, and there's 8-fold subunits that you can see actually here quite clearly. Now, if you compare it to standard resolution, there's almost no comparison, and clearly there's a lot of information that has been gained as a result of this overcoming of the diffraction barrier. Now, if you have a much higher spatial resolution, you can learn new things, obviously. And I would like to show you one example. I think virology is a major area of application for subdiffraction resolution imaging for all the methods, and including also for stat microscopy, of course. Now, in this particular case, we teamed up with HIV experts, the group of Hans-Georg Kreuslich in Heidelberg, and they were interested in the distribution of a certain protein that is found on the envelope of the virus. Now, HIV has a diameter of about 140 nanometers, so it's much smaller than a diffraction barrier of 250. And if you label the protein ENF here and try to image it, you get nothing but a blob of light that is 250 nanometers in diameter. But if you do stat microscopy, then you see that this protein ENF forms a pattern. And this is obviously meaningful, it means something. In fact, if you correlate it in space and with the virus and check out how the pattern depends on the maturation level of the virus, what you will find is that the mature particles, so those that are ready to infect the next cell, have their ends in a single place. They have them strongly focused. There are about 7 to 14 copies of this protein on the virus. So what has been learned here is actually an important step in the pathway of maturation and infection of HIV. And this is just the beginning. I think virology, as I indicated, because of the size of the viruses of 30 to about 150 nanometers, is a major area of application, sorting out all the proteins and how they change over time. This will definitely be possible. Well, this is a snapshot with normal resolution of synaptic vesicles in the axon of a living cell, but this is now stat, and now because the resolution is higher, you can see the movement of the synaptic vesicles here in the axon of a living neuron. I'm just indicating to you that you can take time sequential images, so this is a movie that, that has been recorded in here. Now, of course, live cell imaging at the extreme is to go straight to a living system. So in this case, it's a living anesthetized mouse where the skull of the mouse was open, and we looked into the upper layer, the molecular layer of the brain. Now, this was a transgenic mouse. So some of its neurons expressed a yellow fluorescent protein, so that it was highlighted by the presence of a protein. But here on the left and the right-hand side, of course, the brain tissue was not labeled, and this is why we can see this single neuron here outlined. But the resolution here and seeing the dendritic spines is due to the fact that we do stat microscopy, so we can see them much more clearly because of this high spatial resolution. And not only that, we can get time sequential images here. You can see this is a movie. We see that these dendritic spines change actually over time. You can see that this spine neck and this cup-shaped form. This is just the beginning. I'm convinced that in the not-too-distant future, we will be able to see protein distributions here directly at the synapse, and at some point, it will be possible to give, for example, a visual cue to the mouse and see what's going on directly in the synapse. This is apart from the visual cortex, so this is taken actually from the visual cortex of the mouse. And this is very exciting because it should be possible to get fundamental insights about how neurons interact with each other at a molecular level. Now, this is just to show you that you can also take three-dimensional imaging. You can focus into the brain tissue, for example, and have super resolution, so to speak, in 3D, X, Y, and in Z. And that allows you to make this rendition. In this case, it's the actin here resolved with very high clarity. You see the rings in here in these dendritic spines. Now, after these applications, I'm coming back again to the basics, to the resolution. And so the question that comes up most naturally if you work on the resolution is, what is the resolution limit that we have now? What type of resolution can we achieve, at least conceptually? Now, this question is relatively easily answered if you go back to this implementation of this concept, and the resolution is obviously given by the region D in which the molecule is allowed to be on, in which it is allowed to assume the on state. And if you don't have the red light, it's given by Abbe's equation, but if you increase the intensity, so the intensity at the donut crest goes substantially beyond the threshold intensity, then the D becomes smaller. And, of course, the resolution is now higher than in Abbe's case. And so we have to do something about this equation. And if you make the calculations very simple, or if you measure it, you will find that D scales inversely with the square root of this ratio I over IS. And this is something like a number of 4, 5, 10. You see the ratio in here, or even higher. The unit is here so that we don't divide by 0 if I is 0, so if you remove the donut. But the good news here is that if you increase the intensity, D goes down in this equation at least to 0. Now here we can't separate the two molecules because they are allowed to emit at the same time. But if you make it such that only one molecule fits into this region in which the molecule is allowed to assume the on state, then we have a true molecular resolution, meaning that in this concept we can separate two molecules that are at molecular distances. So here we see the signal from here, and then how we get a neighboring molecule, we move the beam like that just to turn off the other one, the neighboring one, and so we can separate because they are made to force to emit sequentially. By the way, if we manage to keep this pitch black, at least in the concept we can, no photon coming from here, but only from this molecule. One photon is enough. That's enough, because then we know there is a molecule and that's it. The position here, where the molecule is emitting or not emitting, is precisely determined by the many photons that we put in here. So the photons here determine, the red photons determine actually the position of recording the position of the molecule. And if you have one signal, one photon in the concept, that's enough. We can go to the next, and so on. Okay, now you may ask, can you get this molecular scale resolution? Well, in the concept, yes. It's clear. But in practice, of course, currently with organic molecules, that's not yet possible. So the standard resolution is STET microscopy. Depending on the fluorophore use and, of course, the implementation of the concept, you range something typically between 20 nanometers, 30 nanometers, sometimes 40 nanometers, depending on the fluorophore and also on the chemical environment. But it's possible to demonstrate a much higher spatial resolution with inorganic fluorophores, so to speak. So these are defects in diamonds. These are so-called charged nitrogen vacancies in diamond. They fluoresce. If you excite them with green light, they emit in the red. And they can be turned on and off as many times as you want. There is no photobleaching. There are no competing transitions taking place, but excitation and de-excitation by stimulated emission. And then you can make, say, out of this, you see, you make regions of emission that are down to the single-digit nanometer regime, so down to, say, 2 to 4 nanometers, and this shows the potential of the concept. And here, the wavelength was 775 nanometers, so this is a small fraction of the wavelength, so it's below 1%. And this can be made even better. You can even improve on that. Now, this definitely is a nice proof of principle experiment to show you that this goes further and further and further, but it's not just that. In fact, the so-called charged nitrogen vacancies are now a hot topic of research in quantum optics or, atomic solid-state atomic physics, or I don't know how you would call it, because they have a very interesting feature. They have a spin state that has a long coherence time at room temperature, and it can be read out optically. Prepared optically and read out optically. And therefore, these are hot candidates, these charged nitrogen vacancies, for magnetic sensing at a nanometer scale, optical sensing in the end, and also as qubits for quantum computation at room temperature. And maybe one day, STAT microscopy will be used in order to read out magnetic fields, perhaps even from protons, single protons, and then hopefully perhaps even protein structure can be read out using this as facilitators, or that could also potentially be used to read out the qubits in a quantum computer. This is just to show you there is more than just the distribution of a flow of proteins to be seen. There's a lot of applications. Now with that, I'm coming back to the basics. I explained the name of the game of STAT microscopy is to play on-off with these basic states, S0, S1. This is the most basic states in the fluorophore. They're found in any fluorophore, so STAT is applicable to any fluorophore, on-off. But if you realize, and I realized that day one, this is not just about stimulated emission. This is about having two states playing on-off with the fluorophore. Then you know there's also alternatives. What did I do? I checked out open textbooks to see what other states are in the fluorophore. And the only reason why this came out in '95 is that I had problems publishing this paper. Suggesting as an alternative to STAT that one could empty the ground state, so to speak, and pump it to a metastable dark state. Push the molecule to a long-lived dark state, and then take it out of this system, and then you have this as a dark state, and say the normal excited state as the on state. So this is an alternative. Well, there's another alternative. You check out chemistry textbooks, then you find, there's cis-trans photoisomerization, so you can use, there's a relocation of the atoms, so to speak, and then you can use the trans state as the off state and the cis state as the on state, and if you push them back from this state to the other state and vice versa, you can create differences in states using cis-trans isomerization. And now, you may ask, why are you interested in this? This is very special. I mean, not all fluorophores isomerize, obviously, and this is also, if you have some specific knowledge, very much dependent on the chemical environment. So why do you use these special states? Well, here's the answer. If you look at the lifetimes of the states involved, you see that here you have nanoseconds, here you have microseconds, and here you have milliseconds. So the lifetime of the involved states increases by orders of magnitude. Now guess, why is this important? Why was I interested in this long-lived states? It's very simple. We separate adjacent features by having the neighboring molecules in two different states. But look what happens here. Here, the state, the on state, lasts only for a nanosecond. So after a nanosecond, this difference in states on-off disappears. So I have to hurry up preparing this difference in states, and I have to hurry up reading it out. Because after nanoseconds, this difference in states that I critically need to make the separation is gone. But here I have more time, microseconds, here even more time, milliseconds. Here I can switch it off, it stays off, and then turn it on, and this difference in states lasts for much longer. And because it lasts for much longer, I don't have to hurry up putting in photons so quickly to create it, or reading out photons so quickly to know the difference, or to see the difference. And so the longer the lifetime of the states involved, the lower is the intensity requirement. The fewer photons I have to put in per unit time. Or to speak more formally, the intensity threshold, IS, scales inversely with the lifetime of the states involved. And the longer the lifetime, the lower is the intensity requirement. So megawatt per square centimeter, kilowatt per square centimeter, and watt per square centimeter. And this is, of course, extremely useful. You can reduce IS in here, so meaning the threshold is down. That means you can get a same high spatial resolution at much lower light levels. This is good because you don't have to put in photons per unit time. You can reduce the load, the intensity load on the molecule. So this is very good if you if you want to image living cells over extended period of time. By the way, I would like to mention, it's not only the megawatts, kilowatts, or watts per square centimeter that matter, it's also the cross-section of interaction. So even if that may sound high to you, it doesn't matter if the cross-section of interaction with the molecules is low. We are flooded with neutrinos all the time, but it doesn't matter because they just pass by. So just to mention this to you, it's not only the kilowatts or the megawatts that matter, it's also the probability of interaction. But anyway, it's always better to reduce the load. It also has another reason why it's useful to go down with the intensity. If you need very little light, you can say, oh, I can use a cheap laser, for example, and spread out the light over a large field of view. And so you can use, for example, you can make, for example, many donuts. You can have an array of donuts taken from a cheap, continuous wave laser, and then play this game, for example, with the cis-trans isomerization. And the cis-trans isomerization is, of course, very handy because it is found in so-called switchable fluorescent proteins. And WE discovered actually in '97 that you can switch GFPs. Now, since then, many people have perfected this switching so that you can do it many times. And already in 2003, there were, say, fluorescent proteins that where the switching could be controlled very easily. And so I was very excited at that time, 2002, 2003. Oh, let's do this STAT type of thing at low light levels or large field of view using this cis-trans isomerization with so-called switchable fluorescent proteins. And of course, you can use many donuts in parallel if the distance is larger than Abbe's barrier, because then the signal that is produced here by each of these donuts is not confused at the detector. So there's no problem in parallelizing things. It's not that you have to use a single donut. This was clear from day one. You don't have to scan over the large field of view with a single donut. You can parallelize it as long as the donuts here are further away than the diffraction barrier. No problem. You can always sort it out. But you have to read out, so to speak, the camera for every single scanning step. So you make the image by taking the summation of many images on the camera, because it's a scanning procedure. Now, if you make 10 steps or here and 10 steps in this, you may be able to cover the whole field of view, so to speak, with the many donuts, depending, of course, on the spatial resolution. And then, of course, you can record a large field of view. In this case, it's a living cell. In 2 seconds, with more than 100,000 donuts, 110,000 donuts were actually used here, to be precise. Now, the reason why I'm showing you this, not only that the development continues, the molecular transition here is critical. We are able to have this low intensity recording at high speed, highly parallelized. Why? Because we have chosen the right molecular transition. So the molecular transition, the type of molecular transition, and the kinetics of the transition critically determines the performance of the microscope, not the objective lens and so on. This is, in the first place, what determines this thing. So, next question. What does it take to get the best resolution? Now, let's assume you had asked this question in the 20th century. So here it's saying 20th century. Well, the answer in the 20th century, I'm sure you know it, would have been, oh, I need good lenses. I have to go to the big companies and hopefully they give me the best lens, and with the best lens, I get the best clarity. That's very obvious. Why? Because the features were separated by the phenomenon of focusing light. And the better you made the focus here or there, the better the separation. So you're totally dependent on the fact that the focusing is very good. That's fine, but it has one problem. It is limited by diffraction, because even if the lens is perfect, so to speak, in the end you're limited here by the phenomenon of diffraction. So what was the solution to this problem? Yeah, if features come close and your diffraction limit, you don't see them, you cannot separate it. So what was the solution? Well, the solution was do not separate by the focusing of light. Separate by placing the molecules of the adjacent features at the time point of detection in two different states. By making sure that at the time point of detection, the molecules of the adjacent feature are two different states, you can tell them apart. And here you have a choice of states, as you can see here, S0, S1, or cis or trans, and this allows you to tell things apart. Now, you've seen it here in STAT microscopy and RESOLFT and the related methods. You have a pattern of light that determines where the molecule is on and where the molecule is off, using a transition that gets it from one state to the other. So here, the position of the on and the off state is tightly controlled by the incident pattern of light. So this is a hallmark of this STAT and resolved related method. Now, it's interesting to compare it with the seminal discovery and development by Eric Betzik, the palm microscope, which is firmly based on the discovery by W. Myrna that you can detect single molecules. Again, here we have a diffraction zone, but here, and that's a fundamental difference, you use single molecules, the fact that you can detect single molecules as a critical ingredient. And not only that, you make advantage of the fact that if you have just a single molecule here, you can identify it and separate, of course, features just by turning on single molecules. But the difference here is, here the position X, Y, Z, here in the palm, is not tightly controlled. This is the elegance, the beauty actually of this concept. It is coming up stochastically. So here, another molecule is coming up, then you turn it off. Another molecule is coming up stochastically, and you turn it off again. But then you may ask, how do I know where it was stochastically turned on and off? I don't know the position or coordinate well. It can be sorted out in a very elegant way. You put in a detector that has a coordinate, namely a camera, and that's a condition, if the molecule is capable of producing a pattern of light, so producing many photons here at a camera, you can use this pattern of light to identify the position. Without going into the details, it means you can calculate the centroid here of this pattern by using many photons. The more photons you have, the number of photons, the more precise you can find out the position of this on-state molecule. And you look at this here. Here you also need many photons. So in order to define a position or to find out a position, you always need many photons. It's very important. Why? It's not surprising, because we have diffraction. If you have just one photon, and this is diffraction zone, the photon will go either here or there, totally uncontrolled, or there or there. And only if you take many actions, or interactions, and many events, you can in the end define or find out the position with high precision. The more photons you have, you see this is the brightness here, the more better you can define it. You're not confined to using just a single, of course, donut, as I mentioned. And of course, here you're not confined to using just a single diffraction zone. You can easily have a wide field arrangement. So I showed it already, the blue pattern. So here, of course, we have an array of donuts. And then, of course, again, the fundamental difference here, the position of the molecules of the onset is tightly controlled by the pattern that we put in here. We can have here one molecule, three molecules, doesn't matter because the position is controlled. Here, one molecule within the diffraction zone, so they are further away than the diffraction barrier, totally randomly. You just have to make sure that they do not overlap in space, but they are completely randomly. Here, the position is determined by the pattern of light that goes in, here with the pattern of light that comes out. And here, it's also interesting, another insight. What does I over IS stand for, actually? Now, I said, IS is the number of photons that you need to make sure there is one photon interacting with the molecule. So this I over IS is, so to speak, the number of photons that really do something at the molecule. If you take this ratio, and here, this is the number of photons that really do something at a detector. So you need photons that do something. And this is actually I think the beauty if you make this comparison, it shows actually the importance of the number of photons very, very clearly. The separation of the features in both cases is done by an on-off transition. So this is critical to tell things apart. So in fact, the super-resolution field is based on the fact that you have two states, at least two states. You can also have three or four, so to tell things apart. In the easiest case, it's on-off, fluorescent and non-fluorescent. And so, in the 20th century, it was critical to have lenses, as I indicated. So the lens makers were actually those people who were totally decisive and critical. And so you went to company X and company Y to get the best lenses. But now, it's not the lens makers anymore, definitely not. So what we do here is we utilize molecular states. That's what we do. Molecules, the molecule is critical. The molecule, in the end, determines the total performance of the system, the spatial resolution, the speed, the brightness, the contrast. The molecule is absolutely critical. And molecules, that's not optical technology, that is chemistry. In simple words, you can say, it's the chemists, it's the best chemists that give the best spatial resolution, and not the optics anymore. So this is a fundamental transition because of the fact that we use molecular states for separation. In a way, you can say, no doubt, breaking the diffraction barrier or the diffraction barrier was a physics problem, full stop. We don't have to rephrase that. But now it has been converted into a topic of chemistry. And the story is not over yet. As I said, you need two states. You can say fluorescent and fluorescent. In my view, it's not a coincidence that this was the first type of transition that was used to break the diffraction barrier, because a fluorescent molecule can be easily disturbed. You can easily turn it off and brought back to the bright state again. And honestly, if I had found a way for non-fluorescent things already in '94, I would have done it. It's not that I was tightly, say, attached emotionally to fluorescence. No, it was easier to do with fluorescence. That is the point. But once you realize that, I can also use other types of states, absorption, non-absorption, then you could come up with a super-resolution absorption microscope or a super-resolution scattering microscope, spin up, spin down, or the attachment of molecules can be perceived as a state, like in a method called paint, where you have a binding state and an unbound state. And so the method development goes on, and with that, actually, I'm coming to my acknowledgement slide. So I was fortunate to work with many people that I managed to keep passionate about these things. They put in a lot of effort, a lot of ideas, and this is certainly one of the ingredients of this success. And they keep on going. They keep on going because, as I said, this story has just begun. And with that, I'm coming to my final slide. Well, Abbe's equation cannot explain the situation anymore. That's obvious because we can separate features in here. We know exactly what we have to do. We can plug in this square root factor. And now, this is good news because D goes down to 0 in this equation, meaning to the size of a molecule. The molecule, so to speak, is the limit of separation because that's the quantum entity that we have, that we take for separation. Now I have a final question for you, but I'm sure you know the answer. Why can't we separate this fiber from that fiber, but here it wouldn't be possible? Well, at the time the molecules of this fiber were on, the molecules of that fiber were off, and at the time those were on, the molecules of that fiber were off. Sometimes the solution to a 100-year-old problem can be shockingly simple. Thank you very much. Thanks. Sure.
Thank you very much, Professor Hell. Fantastic lecture. In interest of time, we will not have a chance to have any questions right now, so I will have the pleasure to introduce our next presenter. Please, Professor Mörner, join me on the scene here. Professor Mörner grew up, as I understand, in Texas, Pleasanton, and had a fantastic career over the years in physical chemistry, molecular biology, and also working with chemistry, as you heard, the key of everything. And of course, we say that coincidences are very important in science, but I think hard work is extremely important. And yes, rigging up the computers here. And I know that Professor Mörner had the chance to collaborate and also be inspired a bit by the work of Roger Zien, a Nobel Laureate.